Let's see if we can get through 9.4. Remember, today was all about quadratic, exponential, proportional relationship, or non-proportional linear relationship. Remember, proportional is also linear. Write your name and your period. All right, let's take a look. Here's my y-axis, here's my x-axis. Where the y and the x-axis meet is the origin. So does this go through the origin? No, so it's not proportional. Is it a straight line? Yes. So a straight line that does not go through, a straight line that does not go through the origin is non-proportional. So this one's linear, non-proportional. Take a look at this one. Straight line but goes through the origin. That means linear proportional. Easy. Here it is, quadratic. If it looks like a U, you've got quadratic. Look at that. There's a U in quadratic, and the shape looks like a U. All right, let's take a look at this one. Okay, this one we've got, is that linear? No, so we can get rid of the first two. This is non-constant rate of change quadratic or non-constant rate of change exponential. What's this one going to be? See how close it gets to this x-axis but doesn't actually touch it? Well, that actually touches it. I'm not sure about that one. Because it touches it, I'm going to assume that it keeps going and comes back up. So I'm going to say quadratic. This guy, see how it comes down and never touches the x-axis? That means that's exponential. This guy is a straight line and doesn't go through the origin, so it's linear, non-proportional. All right, let's see what's next for us. These examples show common errors in working with rates, so these are wrong. Each problem contains an incorrect conclusion. Explain why each conclusion is incorrect and provide mathematical evidence to support your answer. All right, let's see. Since the rate of change is constant, the data is linear. Well, they didn't find the rate of change, did they? They found the first difference. But let's go ahead and find the rate of change. To go from -1 to 2, you have to add 3. To go from 2 to 4, you have to add 2. And to go to 4 to 5, you have to add 1. So the rate of change for this one is 2 divided by 3, which is 0.66 repeating. The rate of change for this one is 2 divided by 2, which is 1. And the rate of change for this one is 2 divided by 1, which is 2. So the rate of change is actually not constant, and so it's not linear. So the rate of change is not constant, so it's not linear. I know in class we talked about how it's the first difference, but look, these don't go up by the same amount each time. If these don't go up by the same amount each time, you have to double check each rate of change. Remember, change in y over change in x equals rate of change. All right, let's try the next one. Since the rate of change is constant, well, let's take a look. From here to here is 5, here to here is 25, here to here is, here to here I had to add 100. So 5 divided by, oh wait, sorry. Oh, look at their mistake. They found the difference over here. So they made a mistake in the rate of change. The rate of change for this is the change in y. Look, they used the actual y, 5, 25, 125. So let me recreate this table and let me show you what the rate of change actually looks like. If you were to find the rate of change, it would be the change in y over the change in x. The first change in y was a positive 4. the first change in x was a positive 1. The next change in y was a positive 20. The next change in x was a positive 1. The next change in x is a positive 100. Next change in y, next change in y was positive 100. Next change in x is positive 1. So look, 4 divided by 1 is 4. So the rate of change was 4, then it was 20, then it was 100. This is non-constant rate, so it has to be non-linear. Okay, next one. Since the x's do not increase by 1, the data cannot be linear. Well, that's completely wrong. To be linear, it has to have a constant rate of change. So let's do this. To get from -3 to 1, I had to add 4. To get from 1 to 7, I had to add 6. To get from 7 to 9, I had to add 2. So let's find the rates of change, which is the change in y over the change in x. So the first change in y was a 4. The first change in x was a 2. The next change in y was a 6. The next change in x was a 3. The next change in y was a 2. Next change in x was a 1. 4 divided by 2 is 2. 6 divided by 3 is 2. 2 divided by 2 is 2. So that means you have a constant rate of change, which means it is absolutely linear. We have a constant rate of change. Remember, the rate of change is change in y divided by change in x. Change in y divided by change in x. Change in y divided by change of x. That means it's a constant rate of change, which means it is linear. All right, this one. So they said the change in y over the change in x, which is the correct rate of change. But they said the rate of change is 2. Look at their first one. They put 2 over 1. Look at the next one. They put 3 over 1.5. Look at the next one. They put 6 over 3. See what they did? It should be y over x. So if we did the change in y over the change in x, the first change in y is 1. The next change in x is 2. The next change in y is 1.5. The next change in x is a 3. The next change in y is a 3. And the next change in x is a 6. So 1 divided by 2 is 0.50. 1.5 divided by 3 is 0.50. 3 divided by 6 is 0.50. So this has a constant rate of change, which means it is in fact linear. All right, one thing on this staying sharp. For the ratio of width to length, you want width to length. The width of this one is 1, and the length is 2. The width of this one is 2. The length of this one is 2, 3, 4. So let's look. 1 divided by 2 is 0.5. 2 divided by 4 is 0.50. And let's do the last one. The width of this one is 3. The length is 6. 3 divided by 6 is 0.5. The next one, 3, 4. The width is 4. Follow it up. That means the length is 6, 7, 8. 4 divided by 8 is 0.50. So it says, are these rectangles similar? Well, the ratio of width to length is the same, so yes, it is similar. All right, give the rest a try.